we go. So today we're going to speak about the topics of conjugacy, an all-important topic in dynamical systems that allows us to declare two dynamical systems similar in some sense. We'll see in which sense for linear systems first. And then semi-conjugacy, which basically says that we can declare one system as similar to a subsystem of another. And that semi-conjugacy is intimately connected to the concept of model reduction, where we ask the question, can we find observables such that an initial dynamical system that is described by n states can be described effectively by some smaller number m as states, and then also describe the meaning, because obviously if you're defining something by a smaller number of states, some of the dynamics might be lost. So we'll discuss a little bit in which sense elements of the dynamics are lost. And then we'll talk about the concept of isostables as well, an important concept that arose from strictly from Koopman operator analysis, and is a geometric concept in dynamical systems that is being used quite a bit, both for analysis of dynamical systems, but also for design of control for dynamical systems. So let's start with the notion of conjugacy. So if we have two linear systems with matrices A and B, then a conjugacy is defined to be an invertible linear mapping H from the space Rn to itself, such that when we apply H to the flow of the system driven by matrix A, that is equal to first applying H to the same initial condition x0, and then applying the flow of the second system to it. Maybe I can draw a little picture here. It goes something as follows. Say we have a dynamical system that is driven by matrix A. That really means it's just x dot is equal to AX. And then there is another dynamical system driven by matrix B. Now let's say we start from x0 here. And we flow forward. And that flow takes us to this point here, which is e to the AT x0. So let's do two maps. This one, or two links. This one starting from this point under H. H is a mapping that takes any point in this space to some point in this space. Well, let's also do another one that maps x0 to some point over here. And then let's draw the flow. This one here is e to the b t. Okay, so that's the idea. The idea is if you can find H such that mapping x0 by H first, and then mapping it forward by the flow e to the bt, so it's this part here, is exactly the same as taking x0, mapping it by flow of this dynamical system e to the at x0, and then using H over there. If that H is an invertible mapping here, in linear, in this case, we're going to call it a conjugacy because it's a linear mapping. It's also clearly smooth. You can take a derivative. No issues with that. You will see in nonlinear systems, we are going to be very interested in various aspects of smoothness of that H, but here we're just asking for it to be a linear system. And so, so the way H is found is you exhibit a matrix V such that H is similar to B using V. So V is some non-degenerate matrix such that V inverse BV is equal to A. And if you plug that in here, so you plug E to the V inverse BV, it's easy to see that E to the V itself, so H of X is equal to Vx is just that required conjugacy. So, since similar matrices have the same eigenvalues, then the spectral expansion of these two systems is similar in the sense that the eigenvalue part stays the same. But let's now see a little bit about eigen functions. So, so let's talk a little bit about eigenvectors, because if we have similar matrices, then the eigenvalues are going to stay the same. Let me erase this. So let's assume that we have distinct eigenvalues just for simplicity. And let's assume that Vj and Wj are the eigenvectors of A and A star, the adjoint. And then AVJ is lambda JVJ. Now rewrite A as V inverse BV. So we are assuming that we have a conjugacy that is given by H is Vx. So V inverse BV acting on Vj. Now multiply from the left by V, and we obtain that BV Vj is equal to lambda JV Vj. So clearly this vector here, which is matrix V acting on Vj, is actually an eigenvector of B. So eigenvalues stay the same. Eigenvectors change from Vj's to V, capital V, Vj's. And then the dual eigenvectors change as follows. Let's take the adjoint operation on V inverse BV. We obtain V star, B star, V inverse star, Wj. So we know that A star Wj is lambda JC Wj, that's by definition. And then we obtain, by multiplying from the left by V inverse star, that B star V inverse star Wj is lambda Cj V inverse star Wj. In other words, if phi j is x Wj's, and we know that V inverse star Wj by this relationship here is an eigenfunction of B star, then psi j, defined as inner product of x and V inverse star Wj, is an eigenfunction of the Koopman operator associated with a linear system B. So eigenvalues stay the same. Eigenvectors map in a simple way. So now we're going to restrict, weaken a little bit our requirements on what the mapping between these two spaces, that mapping H, needs to be. So we're going to talk about semi-conjugacy, not conjugacy. So let's work again in a simple situation where lambda1, lambda2 to lambda n are real eigenvalues, and they're all, let's say, less than 0. So we have a stable system. They're all real and less than 0. And then let's take eigenfunction phi1 associated with eigenvalue lambda1 and define a new quote unquote coordinate. Y is equal to phi1 of x, right? That's a coordinate on the state space. And the linear dynamics is obviously phi1 dot is lambda1 phi, or in terms of y, y dot is lambda1 y. So what did we obtain? Just by using this mapping from X to space of real numbers R obtained by phi1, we obtained a one-dimensional linear system. So this is somehow a simplifying coordinate on the original system. Remember, the original system might have been x dot is equal to ax, where A is some full matrix. And if you find an eigenfunction, you now transformed it into a linear one-dimensional system. So this can be thought of in terms of what we call a linear semi-conjugacy. So an m-dimensional linear semi-conjugacy is a mapping HNM. N stands for the origin space, M for the destination space. You go from Rn to Rm, where M is strictly less than N, such that the same relationship as the conjugacy that we talked about before holds, but now this C is not an n by n matrix, not an n by n matrix, but an m by m matrix, right? So HMN maps an n, like in Nancy, dimensional vector to an m dimensional vector, but the rest is similar. So if I take an initial condition X, advance it by the flow of A, and then map, that's exactly the same as taking X, mapping it by H, and then advancing by this lower dimensional flow. That's the idea of the semi-conjugacy. Okay, let me give you a pictorial description. So here we are in a three-dimensional space. This is a trajectory in a three-dimensional space. And so here is my semi-conjugacy. In this case, I actually did use the eigenfunction phi1 to provide a one-dimensional conjugacy. I start from X and map it here. That's phi1 of X. And then I go along the trajectory and I find myself over here. And I again map by the value of phi1 at that point. And I find phi1 of STX. ST is the flow on this space, yeah? And in our case, currently, what we're discussing, that's a linear flow. So this would be e to the a t x. But the point is that phi1 has linear dynamics. So phi1 dot is lambda 1 phi1. So if I know the value of phi1 at the beginning time, I'll know the value of phi1 at any later time. And that is valid for any x whose initial value of phi1 is exactly the same, right? So I can map a whole plane of initial conditions x into a single point by the value of phi1, because phi1 itself is geometrically defines a plane, right? Remember, my eigenvalues here are real. So that's just a constant value of this inner product is going to define a plane, and this whole plane is being mapped into that point. So that's the information that you would lose if you would just consider the evolution on this space that is, by the way, called quotient space, for the reason that we are taking a quotient, we're taking all the points on which we have the constant value of the eigenfunction into a single point. And then we're just evolving that point. But we really don't know, after we pass to this space, we really don't know where the initial condition in the rest of the space was. So in data science terms, this would be a encoder with loss. So we lose some information if we throw away everything about the initial condition and only understand the evolution in the conjugate, or rather semi-conjugate space. But taking that aside, the construction is precise. You know exactly what the encoder is giving you. You know precisely what you lost, and you know that the evolution on this space is rigorously going to be described by the equation phi1 dot is lambda 1 phi1. So in this sense, we have reduced the model. And I'll talk about that a little bit more in a moment. So let's talk about eigenvalues and eigenvectors. If Vj is an eigenvector of A with eigenvalue lambda j, then let X to be Vj, and let's plug it into this. So Hmn e to the atx, if X was Vj, e to the at acting on Vj, Vj being the eigenvector, gives you e to the lambda jt Vj. E to the lambda jt goes out, so that's e to the lambda jt Hnm Vj. Hnm is my linear conjugacy. But that, I mean, sorry, this by definition is exactly e to the ct Hnm Vj. So if you look at this, you're going to see immediately that this vector Hmn Vj, which is the nm, as in Mary, dimensional vector, is in fact an eigenvector of the matrix of the dynamical system that is defined using the matrix C. So as before, the eigenvalues of the reduced system or of the conjugate, in this case semi-conjugate system, are the eigenvalues of the original system. It's just that they're not all of them. You're going to have m eigenvalues for the reduced system and n eigenvalues for the full system. So you have thrown away some eigenvalues in the process. Now the eigenvectors for the eigenvalues that you didn't throw away are defined by this expression here. So you just apply the semi-conjugacy to the vector itself. Okay. So we proved that the eigenvalues of C are a subset of eigenvalues of A, and eigenvectors of C are transformations of associated eigenvectors using this semi-conjugacy. And now, as I already kind of pointed out, if you just take Hn1, so the semi-conjugacy, to be phi1, that in fact defines a proper semi-conjugacy. The reason being that your matrix, in this case, is just going to end up being the scalar eigenvalue lambda 1, because we know that phi1 dot is lambda 1 phi1. So that immediately gives us that we satisfy this equation in this form, E lambda 1 T phi1, which we define to be Hn1, is with, in other words, we defined Hn1 to be phi1, so that would be this, is equal to ut phi1, that is by definition of phi1, because phi1 is an eigenfunction of the Koopman operator, so it satisfies this relationship. but that is equal to phi1 composed with e to the atx, because our original system was driven by the matrix A. So that proves that phi1 of e to the atx is e to the lambda 1 t phi1. In other words, this relationship is satisfied with hn1 being phi1 and c being just the scalar lambda 1. So that shows how eigenfunctions themselves can be used as conjugacies. And so the space Rm in general is called the quotient space of Rn under the action of this mapping Hnm. And as I mentioned, what that does is it takes whole classes of initial conditions into a single initial condition. All right, so let's now discuss how this pertains to model reduction. So this is best described on an example to start with. So let's start with a linear system in R2 given by dx dt is lambda 1x and dy dt is lambda 2y, and 0 is bigger than lambda 1 is bigger than lambda 2. So both eigenvalues are negative, but one of them is more negative than the other. And so what is the dynamics going to look like? Well, in Y, we're going to have fast dynamics towards 0, right? Lambda 2 is negative, so that's going to be fast decaying towards 0, fast in the sense that it's faster than lambda 1, than decay in X. So the decay in X is going to be slower. And so the trajectories are denoted here in blue. Now, of course, if your X is equal to 0, then you go towards the origin. But everywhere else, you have this fast decay towards 0 and then a slower slide towards the origin. There are a couple of ways you can consider model reduction to work here. If you wait for a long enough time, Y is going to be really close to 0, right? Let's say that lambda 1 is -1 and lambda 2 is -100 to exaggerate the situation. So e to the -100 times t for time t is equal to 1, that's going to be really, really close to 0. But e to the minus t, well, that's not very close to 0, right? So in X, you're going to have some ways to go, but it's basically going to be sliding along Y is equal to 0. And so for a sufficiently long time, you enter this box close to the origin in this situation, where the dynamics is practically one-dimensional and given by this equation. But there is a little bit more than this local picture. I mean, if you just say, okay, for any Y is equal to some constant, Y is equal to C, consider all these initial points. Consider all these initial points, and all of them are going to be obeying the same dynamics, because this dynamics here does not depend on Y. Yes? So any Y is equal to constant, and I think I reversed it a little bit. Any Y is equal to constant point here is going to be decaying towards Y is equal to 0 in sort of the same way, independently of which X it started with. And any X is equal to constant is going to be decaying to 0 independently of which Y it started from, because X equation is separated from the Y equation. So in other words, when we do the quotient space, we basically take this whole line here of Y's and we map it to a single point, and then we get this equation. Now, this is very simple to see here because I have separated the equations to start with. But in general, for a two-dimensional system with a matrix A, if you just find phi1, the first eigenfunction, and phi2, the second eigenfunction, and their associated eigenvalues. And if the eigenvalues satisfy this, then the equation for phi1 will be d phi1 dt is lambda 1 phi1, and d phi2 dt is lambda 2 phi2. And so in that case, the geometry might change in the sense that you're going to get something like this. So this would be the direction phi1, and this would be the direction phi2. Remember, these are linear functions, and everything is real in this case. And so you would have something like this. So just kind of a curving, not curving, but sort of rotation and stretching of these lines that I have here. So it would look a little bit different, but the principle would be the same, because you would have these lines of constant phi1 that partition the state space. And then you would have lines of constant phi2 that also partition the state space. And if you started on one of these lines, it wouldn't really matter what other coordinate you start with. So if you started on one of these lines where phi2 is equal to constant, it wouldn't matter for exactly what phi1 would be, right? All of them would go towards phi2 is equal to 0 as e to the lambda 2 t phi2. That's the idea, and that connects us to the topic in the introduction that we talked quite a bit about, which is partitions of the state space that are being induced by Koopman eigenfunctions. And you will see that in the nonlinear case, that works for us very well as well. So once you find these eigenfunctions, you get new coordinates on the state space. And in these coordinates, the dynamics simplifies tremendously. And you can actually take one of those coordinates and consider it a model reduction. The other coordinate is not going to, other coordinates are actually literally not going to matter. There is no residual dynamics that you have to worry about once you find an eigenfunction. The level sets of those eigenfunctions are going to be taken together to whatever destination they go. And so to summarize, each set of lines y is equal to constant and x is equal to constant is carried by dynamics into another between various two times. And in the above case, these equations already satisfy the condition to be the eigenfunction equation. So x itself is an eigenfunction, and y itself is an eigenfunction. So okay, so what I was defining here is the partition of the state space, and I argued that these sets of initial conditions that are defined by x is equal to constant go to the x is equal to 0 line kind of concurrently. So in general, it would be nice to find such partitions that would enable you to say that certain sets of initial conditions for a system that is stable to a fixed point, those sets go to the fixed point in a coherent manner together and just kind of shrink onto that fixed point. So I'll show you a movie as to what one of those things looks like. This movie actually comes from a nonlinear system, but just to emphasize the point, you're going to see a lot of dots over here, and those dots are initial conditions. And then watch these black lines here, and watch how the dots move essentially coherently through those sets of black lines to go down to the origin. So that's what you're going to see. There is obviously also some rotational dynamics, but watch these initial conditions and watch them just passing through those black lines coherently towards the origin. If we can find such a set of lines, that is useful to us, because again, we could put all of these initial conditions starting on these one of these black lines in one bucket. For example, if we're not interested in the phase of how they spin around, and we are only interested in the distance from the origin in some sense, we could neglect the phase itself and just consider that one-dimensional motion, right? So from an engineering point of view, very often there are variables of the system that we don't care too much about. They can be oscillating, and it's not necessarily of importance in some given application. Maybe the only important thing is that the radius, for example, from a certain point, distance from a certain point goes to zero. But the problem with defining something like this is that, I mean, in essence, you can put any nested set of lines like this around the origin, and the dynamics is going to take you, if those lines are dynamically consistent, meaning I start from one of those lines and I define the other ones by just pushing things forward. In principle, you can get such a partition. So we require a little bit more. And what we require is that we have the situation in which when you approach the origin, the asymptotic approach to the origin is coherent, or rather that it's in sync with the natural dynamics, linear dynamics close to the origin. Now, of course, here we are discussing it for linear systems, so it's going to be a bit simpler to define. But that's the idea. So in principle, you could set up one of these curves here in an arbitrary manner, and then you could put initial conditions here, and then your next curve would be, after some time, you would define it by just evolving the flow forward. But in that case, you might have some strange approach to the equilibrium as you go on. And so we are going to require that approach, when you go to the equilibrium point, is somehow dynamically consistent. And we are going to call these curves isostables, and we are going to label them with this calligraphic I, with a subscript that indicates the time itself. So let's go to that definition. So we start from a linear system. We're going to assume an eigenvalue eigenvalue is lambda j is sigma j plus I omega j, where sigma j is real, and omega j is real as well. So we're going to assume that each is a multiplicity 1. So we have a simple multiplicity situation. We have a strictly negative part, sigma j less than 0, and we have an eigenvector associated with it of unit magnitude. So the real part is negative. So we have a stable system. The dynamics is going to take any initial condition towards a fixed point, and the flow is ST's e to the lambda to the AT from R cross Rn. This R here stands for time, and then Rn to Rn, right? So you start with some initial condition in Rn, some given time, you map it to another condition, and that final condition is going to be obtained by spectral expansion that we studied in a number of previous lectures. In this case, we have these eigenvalues with multiplicity 1, so we get sum e to the lambda jt phi j vj, and phi j is the eigenfunction. So everything is before. Now I'm going to say the following. Consider the level sets of the absolute value of the eigenfunction. Okay, the eigenfunction itself could be complex, but also we are also, you know, the eigenfunction itself can attain negative and positive values. Here we are, whatever negative values we obtain, we take the absolute value. So we take the positive sign equivalent. And the reason for this is that if we have a situation where you have some lines like what I've shown before, some partition like what I've shown before, and then you have a fixed point here, then your eigenvector v1 could be pointing in the positive direction of your eigenfunction or in the negative direction of the eigenfunction, right? And so we really want to kind of get a picture in which getting from one of these lines to another takes a certain amount of time, tau, and that time is going to be positive. And so this is just a really convenience in some sense, that we are considering the level sets of the absolute value and not the level sets of the eigenfunction itself. But as we proved earlier, if you consider the level sets of the eigenfunction, that's going to give you an invariant partition. We proved that theorem at some point in the lectures. Okay, so we'll consider the cases of real eigenvalue and complex eigenvalue separately. So let's start with the real eigenvalue lambda 1. We're going to define this time tau, which depends on the initial condition, by rewriting an eigenfunction phi1 as a sine of phi1 e to the sigma 1 tau. Yes, the eigenvalue is real, the eigenfunction is real. This is a positive value. And so really, I'm defining tau, but this relationship, because I know the value of phi1, and I know its sign. So that's predefined. Sigma 1 is predefined. The only thing that I don't know is tau, right? So then e to the atx, well, replace phi1 in this expansion here with this expression here. And e to the sigma 1 tau gives you this over here. Previously, I had e to the sigma 1 t. So now I add plus tau. And then this v1 plus minus just indicates that I could have the sign of phi1 a plus or a minus. Yeah. So, so this would indicate two eigenvectors that, of course, one of them is just a constant multiple of the other one, but points in the opposite direction along the same line. And then we have the remainder. J is equal to n. So this is the first term, e to the lambda jt phi j vj. So when t goes to infinity, all of these things by our assumption, right? The lambda 1 is the slowest decaying eigenvalue, the least negative. All of these other things go to 0 faster than this term here. So we are going to approximately be behaving like this first term when time goes to infinity. And that's the key point. That is, you're going to see the level sets of phi1 or absolute value of phi1, they behave under dynamics consistently with this approach to 0 when t goes to infinity. All right. So so here is the definition. Take the set of states that are on the level set of absolute value of phi1. So that would be e to the sigma 1 tau right there. So if you take the absolute value, then the sign disappears and just becomes positive. And so this is the value that you get. And you obtain that set of states by setting t is equal to 0 here. So those states are defined as x is equal to e sigma 1 tau v1. So they're utilizing the direction of the slow eigenvector plus some j is equal to n alpha j's are arbitrary, vj. So to give you a picture, let's say that this is v1, this is w1, the dual eigenvector, and so v2 is going to be orthogonal to w1, yes? So these lines that I'm defining are really orthogonal to w1. They're not orthogonal to v1, except if v1 and v2 are orthogonal, but they're orthogonal to w1. And I call them I tau 1, I tau 2, and so on. And by the way, on this side and on this side, these objects or the level set, the absolute value of the eigenfunction is the same and positive. So anyhow, what this defines, since this is real, is in general, okay, in 2D situation, it's a bunch of lines, but in general, so here is V1, here is Vj, here is V2, and here is W1. It defines a hyperplane that is orthogonal to W1. That's the geometry. Some very high dimensional plane that is orthogonal to W1. And those are your isostables. So those planes, the partition into those planes is the partition into isostables of linear systems. And so now I'd like to prove that that's actually an invariant partition. So let's show that. We define this set, isostable set, as X in Rn, such that X is e to the sigma 1 tau V1 plus minus, plus some j is equal to n alpha j Vj. So far, so good. Let's apply the flow to that set. So another set in the same partition should be obtained by just utilizing the flow on the original set. That's what invariant partitions are about, right? You take one set, you put it into another. And so how does e to the at act on this? Well, act on X, that really means acting on this expression here. These are eigenvectors. So for each of them, e to the at acting on the eigenvector is going to produce e to the lambda j t. So in the case of the first one, that's e to the sigma 1 t. In the case of the rest of them, e to the lambda j t. But if you look at that expression, that's e to the sigma 1 t plus tau. And that gives you just another quote unquote tau. And beta j's are arbitrary. So if you actually take this, if you look at this, it has pretty much the same shape as this expression here, except that instead of tau, you have t plus tau. And instead of alpha j, you have a beta j. But alpha j's are arbitrary, then beta j's are arbitrary. And so this is precisely the same expression, but just a different a different hyperplane that the initial hyperplane has been mapped into. And therefore, this partition, isostable partition, denoted as I tau, is invariant. It's an invariant partition. And another thing that we can say in this case of lambda 1 less than 0 is that it's a non-recurrent partition. So these lines that we have here are going to bunch up towards the origin. And so once you leave that original line, you never come back to it. So that's the isostable partition. The function tau itself is interesting because it has a unit change along trajectories of f. So if you take tau dot, which is f dot grad tau, that is equal to 1. That's easy to show because phi 1 dot, if we replace phi 1 with sine phi 1 e to the sigma 1 tau, then phi 1 dot produces a sigma 1 that comes from here, and then tau dot. And this part over here is just phi1. Then we have sigma 1, and we have tau dot. So phi1 dot from this expression here is sigma 1 phi 1 tau dot, but we know phi1 dot is sigma 1 phi 1, therefore tau dot must be 1, right? So that proves that tau is an interesting physical variable. Actually, it's a variable that has a constant change along the trajectories of f. It's kind of a dynamic time, if you wish. So now you kind of get the picture of how the systems, at least in this case, the linear systems, but as we will see later, that works very nicely for nonlinear as well, kind of how their trajectories evolve in time with respect to these isostables, but more generally with respect to level sets of the eigenfunctions. So if you have 3 eigenvalues that are all negative, and so lambda 1 is less than 0 but bigger, bigger than lambda 2, bigger than lambda t, then if you take a joint level set, x1 is c1 and x2 is c2, first you kind of slide towards x3 is equal to 0. x3 slides to 0 the fastest because it has the most negative eigenvalue associated. Then once your trajectory has achieved that, it slides along x2 to make x2 0, and then goes into x1. So in some sense, if you have enough separation between these lambda 1, lambda 2, and lambda 3, you actually kind of almost have a piecewise dynamics that goes to x1. This is how you can visualize dynamics in very, very high dimensional spaces, visualize a trajectory using these types of ideas. Now, what happens if you have a complex eigenvalue? We need to work a little bit harder. So now we have the imaginary part of I omega j, and instead of phi 1 to be e to the sigma 1 tau, we actually redefine it to be e to the sigma 1 tau, which is the real part, and then plus I theta. So e to the I theta would be the imaginary part. So now, denoting by this calligraphic R the real part and this I the imaginary part, let A is 2 real parts of Vj. Vj is your complex eigenvector associated with this eigenvalue, and B is minus 2 imaginary part of Vj. To see why you need this, expand. This is the part of the spectral expansion that happens when you have an imaginary eigenvalue. So you have Vj e to the I lambda jt, and then you have the complex conjugate of this. And you will see if you expand it into real imaginary parts that the terms A and B show up next to cosine and sine. That's what happens. And those terms A and B have twice the real part and twice the imaginary part in it, because when you sum these things, think of just the real part of this, you get the real part once and the real part twice, right? So when you sum them up, you get twice. Okay. This is why we get 2 in there. And so now the isostables are going to be defined by all points x in Rn, such that they have a fixed tau here, and then they're represented by this object here that we are going to see in a second. You might recognize this already, but this represents an ellipse. If you vary theta, that's going to be an ellipse in a 2-dimensional plane. I'll show you that in a second. Plus the remainder is 3 from 3 to n alpha j vj. So this is again going to be a plane. So it's some ellipse that kind of, for each point on the ellipse, you attach to it a plane. So this object we call let's say a hypercylinder. So they're really higher dimensional generalizations of cylinders. In 2D, they're actually just ellipses, and the video that I've shown you shows you that kind of an example. In 3D, they're indeed cylinders. But in 4D, you would have to imagine a circle to each point of which we have attached a two-dimensional plane, right? So 4D is a little bit hard to think in, and so this is the way you can kind of reduce it to that. The fact that this expression here gives you an ellipse, this expression here gives you an ellipse, it's simple to see if you just say x is a cosine theta sine theta, where the matrix A is 2 times real part V1 and minus 2 imaginary part V1. These are the columns of this matrix. And so, so cosine and sine, this vector, if you change theta, that's going to give you a circle, right? If you change theta on this vector, so this is a linear, this is a matrix acting on a circle, that is going to give you an ellipse, right? So that's why I said that this expression, when you vary theta, is going to give you an ellipse, and this is what ensues. Your isostables are now hypercylinders in general. So this is a good place to stop. Next time we're going to have just a little bit more on nonlinear observations on linear systems. And in that case, we're going to see that we need to jump from finite spectral expansions to infinite spectral expansions. And so that's going to be an interesting breaking point in our discussions of hierarchy of systems, starting from linear systems, going to nonlinear systems with equilibria, and then going to limit nonlinear systems with limit cycles as attractors, and then nonlinear systems with toroidal attractors. So I'll stop there.